When we have a particular soil, let's say this soil here, it will have a certain scale to it. So there's a certain kind of scale of variability, we might say, and we can call that lambda. And we'll call this soil 1. So the question we have in Miller scaling is how we take the information about the particular scale of a media as well as the fluid properties and translate it to a different system, and let's say this is soil 2. So then how do we do that mathematically? So what we do is we identify in each of these a characteristic length scale. And so this is going to be lambda 2. And oftentimes these characteristic length scales will be just taken to be, for example, the D50 of soil 2. Why would we take D50 to be this characteristic length scale? Because it's something we can easily measure. So now what we're going to do is try to connect this change in size to the physical properties of the system. Now we remember that the pressure in capillary pressure is -2 sigma over R. And what we're going to try to do is get all of the scale-related parts on one side. So what we're going to say is, okay, so if I take this R, and what if I multiply both sides by lambda? So I'm going to have lambda P, and I'm going to divide by the surface tension, is going to be -2, and that's going to be a lambda over R. Now what we have here then is on this side we've essentially taken out all there's no fluid properties, and we've removed the dimension of length. What do we mean? This lambda has the same units as R, so this has no dimensional units. And what we've done essentially is scaled out that this is like the magnifying effect, so R over lambda is a constant for each of these, okay? So the radius of curvature, if we had, for example, a wetting surface in here, and it had a little value of R, then if we went here and looked for the similar one, we would say, aha, the R over lambda 1 is the same as this R2 over lambda 2 for similar systems. So a critical thing is that we have this geometric similarity, and here's how we've captured it. So what we now have is something here which is scale independent. So this is independent of the scale as well as independent now of the fluid properties, because no fluid properties show up over here, so it can't be dependent upon the fluid properties. And that, therefore, is how we scale pressure to make it independent of fluid and the media. And so what we're going to do is we're going to call this P dot is the scaled pressure. And so the scaled pressure is just obtained from an actual pressure multiplied by the length scale of our media, which could take D50, divided by the surface tension. Now, the question is, how do we use this? Well, if we had two soils, we know then that P dot, the scaled value, is the same for both soils so long as they're the same conditions, and that's going to be equal to lambda 1, P1, the measured pressure in soil 1, over sigma 1, which is the surface tension of whatever fluid you're using in case 1. And we can say that because it's scaled, that's going to be the same as the same condition in soil 2. And now we can solve for our P2, which is what we really wanted to get. So the pressure that was in the unknown case, in this new soil, is going to be just equal to lambda 1 over lambda 2 and sigma 2 over sigma 1 times P1. So here is exactly how, if we know the pressure for our particular soil, we went to the lab, we measured this pressure, then we'd be able to say, at this pressure, our soil 2 would have the same basic conditions, the same moisture content, for example. So this is what we'd call the scaling relationship for two soils. And in Miller scaling, you can get the same relationships for conductivity, where we have here the viscosity and the length scale squared. Now, is it a surprise we have the length scale squared? Not at all. That comes right out of our consideration of the Poiseuille equation, right? We remember that conductivity had a relationship to R squared, and that's showing up right there, and the viscosity. In fact, that entire relationship could be derived from the Poiseuille equation. another cool one is we can actually scale time. So if we have an infiltration process, suppose we have a horizontal infiltration process, and the wetting front is moving this way, so let's say this is our length scale, then I can say if it took this much time to go that far, I could now get how long it would take to go a new length. Because we would say that just like before, lambda sigma over eta L1 squared, so we'll call these 1, is, and times T1 equals T2 times lambda 2 sigma 2, that should be a 1, sorry guys, over eta 2 L2 squared. So in other words, we have T2, how long it's going to take to get to this new location here, is going to be equal to T1 times lambda 1 over lambda 2, sigma 1 over sigma 2, eta 1 under eta 2, and L1 squared under L2 squared. Okay? So what it's saying is, if we measured this L2, we could tell you how long it would take. Or if you want to know, if it took 1 hour to get here and we want to know how far it's going to get after 2 hours, we simply solve this for L2 instead of T2. So this gives us a basic ability to scale macroscopic processes using the underlying physics of flow of water and liquids in porous media. So Miller's similarity then allows us to scale all of the key pieces, the conductivity, the pressure, and the overarching length scale and time scale of processes using basic information that we have about the soil and the liquid properties.